Okay, so before the break, we were kind of talking about some odds and ends that we ran out of time for last week and filling things in. But overall, y'all have heard me mention before, this class is, well, it's what I still call as a vocabulary class. Just I try to do all the hands-on labs and things because we can learn the vocabulary while doing interesting things on the computers instead of just writing essays and memorizing a long list of words. Seeing situationally, I guess. So the next one is a very important one for learning about computers, because everything we've looked at so far, we've been looking at just that one machine we're on. But a lot of the power we get out of computers, for example, our class right now, our virtual class running across the Zoom call, we could not do that with one single machine, right? That stuff depends on networks. So we need ways to tie our machines together. I'm doing the definition here. So the interconnectedness of machines so they can work together. Last part of that's kind of important. The interconnectedness of machines so they can work together. Because, well, right before the break, I ran one of the commands that I'd mentioned. I wasn't able to put in the, I didn't put in the lab because I couldn't think of any simple questions to do on this. But right off the bat, you'll see there's a bunch of different machines. Those are all local machines. That's all the virtual machines I have running simultaneously on my Windows machine here. So it's actually a Windows machine, I think 3 Linux systems. I think there's an Android system on there too. And at least 2 versions of Windows. But then there's some other machines here. I don't know which one's which, but this one, you see there's all these other machines here, and then all these down here. My computer automatically knows about a bunch of different machines that it can do stuff with. Some of them it's automatically connected to, others maybe not. Might have to build the connection. There's the address. This is the one my router knows is the second machine, but I have several other laptops, and they might know about each other right now, but until we start doing work between, until we actually start doing work between them, we wouldn't necessarily call it a network. That connection, that useful connection between them. Let's see, I'm gonna draw a picture and write some vocab words up here. Some of the most important ones. Well, I'll start with the picture. I'll put the picture over here. So there is a standardization in the pictures. Probably talk about it in detail soon. It's called Unified Modeling Language. And it's an international standard of communication. So an entire language that's pictorial based. That way we can work on with teams in, well, like for Google, there's a huge presence in San Francisco, Hamburg, Germany, Beijing, and the capital of Ghana. I think it's Accra, but I've got that wrong before. Whatever the capital of Ghana is, Google has a huge presence there. So that's the 4 cities where Google has the largest presence. So if we were working for Google and on a team, there's a good chance we'd have team members in some of those other countries. So we need a way to cross the language barriers that we normally speak, and we use pictorial-based language for that. And our standard way to represent users or actors, the human actually interacting with the computer, is through a stick man. And the first one on the list is going to be a client. I'll try to draw a little picture here. It looks like a little laptop. So to start, the user interacts with the client. What I put in my notes. The end machine the user interacts with. Which for a long time was sort of given as the technical definition, but that has changed a little bit because of the way Google puts their operating systems together. So like Chrome OS and Android are actually networks, and the apps running on them count as users, which makes the apps a lot smaller, better for memory. Because if you wrote an app, if you made an app for Android, if you made an app for iOS and you needed to go to the internet and grab some data at some point, you'd have to include that in your iOS app. But for an Android app, instead of including all that stuff about how to go to the internet and get the information, you can just have your app ask the browser, because the apps are users on the network. So the same way you as the human user can use the browser, your app can also use the browser. And then it makes the app smaller and more efficient, things like that. A little bit beyond this, but it kind of, with that being so big, it kind of changed our, it messed up the wiggle room in the definition as it's been given traditionally. The very technical version, when you're going to see on multiple choice quizzes and things like that, I'll underline the important parts. The vocabulary we're taking from here is the client makes request from network resources. So there's that technical version that we need to memorize for multiple choice quizzes and certification exams and all of that stuff. The client is the one that makes the request from resources. I'll put a couple clients out here, so maybe there's another little laptop over here that's not being used right now. We got these couple machines and we need to tie them together. The next big part that goes with the server, or goes with the client, is the server. A server controls connections on the network. Or in particular, the technical definition to match that is it fulfills requests on a network with the desired resource. Fulfills request a network, and I'm going to write that article very big on a network with desired resource. I kind of stress that point because obviously we have lots of networks in our modern world. And a server is particular to the network it's on. So if a server needs to get something from a different network, it's going to have to it's going to have to communicate with the server on that other network. In our picture, it's going to be over here. Our standard image for that looks like a big rectangle. The biggest thing to notice, though, opposed to the clients, where you tried to draw a quick picture of a laptop where we have the keyboard and the monitor, the server is just the tower there, or whatever shape they come in. We usually draw it like the tower, but there's not a keyboard or a monitor or anything on this picture. The only way we can access it is from the client across our network. Is a big difference there. And an analogy to think about what they're doing, these technical definitions, a restaurant analogy works really, really well. And if you go out to dinner and you're the client and you interact with the server in order to get to request something from the restaurant, and the server fulfills it. So to take that analogy further, if you go in Applebee's and order a steak and a margarita, you're going to go in, sit down at your table, tell your server that you want a steak and a margarita, and the server is the one that knows how to order the margarita from the bartender and how to order the steak from the kitchen. And when they're ready, puts them together and brings it back to you, or combines everything that you ordered, retrieves it, asks for it, goes and finds it from either the bartender or kitchen in that case, and then brings it back to your table. A computer server and client is very, very similar. The client's going to place an order, and the server is the machine that knows how to fulfill that order and bring the stuff back to the client. So actually, a restaurant analogy works very, very well for those. Then we need a couple other ways to tie the things together, and I'm running out of my room on my board here, so I'll put some labels. Here's our client and our server, but there's nothing in here about knowing the rest of the network, right? The server can find any desired resource on the network, but it doesn't already know where those resources are. It knows how to find them. The Applebee's example I just made. Your server might not have a clue how to make a margarita when you ask for one, but the server knows they can ask the bartender for that, and they know who to ask for it. Same thing with this. We need a way to connect stuff. And I very quickly ran out of room. It's okay if I erase this side over here with definitions.
Yes.
The whiteboards up on campus are a little bit bigger than the chalkboard I have here. So the next piece that we'll often use is we need a switch. And that is a machine that identifies connected machines. Connected machines. So I'll draw a switch as like a little box here. That's supposed to be a different size box than the one up here. Server's a lot bigger. Switch is just a little thing. And our machines all connect through that switch. And then the switch is the device that knows about everything connected to it. So we haven't really talked about addressing. Addressing is on the next page of my notes. So it gives each machine a numerical address that uniquely identifies each one. So okay, this is address number 1, address number 2, address number 3. I'll start there. So then if the client needs to request something, it's going to just broadcast across the network, says, I need a file that's on machine number 2. 1, 2, 3, 4. So first thing that's going to do is go to the switch, The switch is like, okay, that's a request that needs to go up to the server. So it's going to tell the server that machine 1 is looking for a file that's stored on machine 2. That's going to come back through the switch, ask how to contact machine 2, come over there, find that file, then bring it back to client 1. So the switch is the one that knows all those, knows the addresses of every machine that it's connected to. And then next to the switch, and there's going to be another piece called a router. It's like a switch, only for networks instead of devices. So also connected to that switch is going to be this piece called a router. And the router does a similar thing to the switch, only it knows about other networks instead of other devices. On your home internet, you probably have a switch and a router combined into one device. But when you get to really, really big networks, more complicated networks, it's actually a lot of people do it in their home networks these days. As networks grow, it becomes more and more important to separate those devices. But most of us have a router switch combination running our own network and just bypass the server part altogether. But that's the main starting pieces we want to know about: the client, the server, the switch, and the router. And those are the different type of devices used to form a network. To tie all of our machines together, each one has a different purpose. So the clients are the end user, or the things that make a request from the network. We ask for stuff, kind of like a restaurant. The client is the customer. Us, when we stop in a restaurant to get dinner, we're in the building. We're in Applebee's, for say, and we're there where the food is, but we can't order it ourselves. All we can do is sit at the table and tell our server that we want to get certain things. We want certain things, and then the server is the one that knows how to navigate around the network, find the stuff we want, and bring it back to us. Is the starting idea of how we build up a network. Really, it's just those 4 vocab terms is what the starting point of what we're looking at here. I believe every single degree program has to take at least one networking class. So you'll see that in much greater detail soon. Still in kind of preview mode. It's okay if I erase this and move on to our networks. Okay.
Yes.
So that's a couple of our components. That's the main parts of our components. Obviously, there's other things we need, like how do we connect it? Different wires, some Cat5 cable, fiber optic cable, Wi-Fi signals. Lots of different ways we can form those connections, but those are details that we'll work in the future class. That everybody has to take at least one networking course. There's one network that stands out above others, though, right? Well, when we have networks, I erased my left. There's different ways we can network things together, and they're labeled the same way as our road systems. So we could have an internetwork. I should write this bigger. could have an intra-network or an extra network. Oops. Spelled that wrong altogether. Extra network. It's kind of like our highway system in America. We have the interstates and intrastates. We know those a lot more often, right? Interstate is between the states, kind of like I-65 in our area here around Louisville. Actually covers a lot of states. It starts in Chicago and goes all the way to Alabama. So it covers, it might not start till we get to Indiana, but last time I was up there, I think there's still signs that say 65 when you're actually in Illinois and Chicago. So from Illinois, Indiana, Kentucky, Tennessee, down to Alabama, between the states, we have that thing. And same thing with networks. We have inter networks that go between networks. They connect different networks together, just like the interstate connects different states together. With a highway system, we also have intrastates, which are inside, internal networks. So that'd be like in your build, ones that don't leave a building, right? If you go up to our campus there in Sellersburg, we have 2 different buildings. Actually, we have 3 because there's one in Clarksville too. So the IT department there at Sellersburg is in charge of those networks in each building, but each building does have its own separate, semi-separate network, right? They're all tied together, but there's different routers producing Wi-Fi signals and different servers inside each one of the buildings on campus. And obviously the one in Clarksville, because that's a long way from the one that's 10 miles from the ones in Sellersburg. So in the internal network, and we have the same thing with roadways. Most people kind of pronounce it wrong. Like in the area around Louisville here, there's an intrastate 265 on both sides. Has the same number, and people just kind of pronounce it like the other one, but the one that does not cross any state lines. Like in Indiana, 265 goes from I think around Sellersburg over to New Albany, and over across the bridge, 265 goes from the west end. I think it's in Portland where it starts and circles around to the east end, but it doesn't leave the state of Kentucky. It's internal to it the whole time. I still spelled that last one wrong, didn't I? Let me try that again. Extra means external. We don't see that as much with the roadways. There are a few of them. The only one I know of is in West Virginia, way up in the mountains, some big curvy mountain roads. There's a state highway that there's no way it can stay in West Virginia up in the mountain region where it's at. So it has to cross over into, to state lines. But it's nowhere near anything in the other state. It's just way up in a rural mountain region. So even though it's technically in a different state, West Virginia is still responsible for that road. So it's external to the state where that road belongs to. That's the only one I've ever encountered, but there's probably more around the country somewhere. But networks, external networks might be for like customers and clients. Right? We have like here in Louisville, Humana, there's that big office building with all those floors filled with Humana, people managing their database and actuaries and stuff like that. And they have an internal network to that particular building. Probably connects to other buildings, which is interconnected to other buildings for a big system, a big company like that. But they're all internal stuff. Only the employees have access to that. So the external one, like all the customers, we need a separate network for them to access. So those 3 words do show up more on the vocabulary. It's like our highways are You may have seen it used elsewhere, but inter is between. Intra is inside. And extra is outside. I can't seem to spell today. Extra is outside. So those three words you will definitely see with networking at times. But this one's kind of different, right? So I just said that's an entire category of things, which if we go back to just English language articles on that, inter network, that means there's a lot of them. So we'd have use the article and inter network, because it's just another of many, many inter networks. But there's something that really stands out as well, right? We also have the internet, and abbreviated internetwork. But the internetwork, the big one that stands out and is just another regular old internetwork. So I'm going to talk about that some and where that came. Sort of there's some concepts there that we just use everywhere now. But yeah, another vocab day. It's okay if I erase these parts. Remember the between, inside, and outside. We have all three types of networks, depending on what we're doing. So, really what I want to talk about is the protocols that is used. So for that one that we call the internet, that stands out above all our other internetworks, it uses a particular protocol to transfer data between everybody. The one we're using right now. It's actually two we're using right now. So internet protocol itself, or IP, it kind of came about in the late 1960s. It's the height of the Cold War. Nuclear weapons kept getting bigger and bigger and bigger. And eventually it hit a point of what we call mutually assured destruction. The Cold War standoff, the weapons had gotten so large, everybody was quite certain that doomsday was right around the corner and it was going to take down civilization as we knew it on both sides. Like, it wasn't like anybody was expecting to win that war. If that would have ever erupted, it was just, everybody was just anticipating complete destruction across the board. But governments being what they are, were determined that maybe they could find a way to stay intact after that and give them an advantage in the Cold War. So the US government in particular, they wanted a communication protocol that could survive mutually assured destruction. A communication protocol that could survive doomsday, basically. So a bunch of researchers got together and started looking at different things. And what they came up with was whenever we need to communicate between two sites, say site A and B, just for some arbitrary labels, there's that communication channel between them, but that's not the only communication line between them, right? Because, well, those are not the only two sites that exist. We're going to have a bunch of other sites out here. So I'll add in a C, and a D, an E, and an F. And along with that communication channel between A and B, the one we actually want to make, there's also these other communication channels. Site C is going to be connected to everything. Site D is going to be connected to every other site. And B, along with that connection we actually want, will be connected to every other site out here. Yeah. And same thing with E and F. So there's that big web. Particular term would be a graph, but this big web of interconnected communication channels. So if we need to make a communication from site A to site B, this line is not our only option. So basically what we do is we check all possible routes and send data down the best option. So instead of just automatically going down this route, so we're going to start here and we send out a broadcast that says, okay, site A needs to communicate to site B, who's available. So we send out that broadcast, and maybe site D is the first one that answers. Site D says, oh, I'm available. So that broadcast gets sent on the site to site B. Then the process repeats. The machines there at site B are just going to say, okay, I have a broadcast coming from site A, trying to get to site B, who's available. Maybe F is the next one to respond. F seems to be, site F seems to be the best route. So B's like, okay, there you go. It sends all the data down there. Same thing repeats. Site F sends out a broadcast like, okay, site A is trying to communicate to site B what machines are available. Maybe this time B answers. So the route from site F to site B seems to be the best route. So instead of just automatically taking the shortest route, the long way to say it is we go ahead and contact every device on the network to see who's available and then send it on the best possible route. The short way, as far as what goes in code, is our machine will ping every machine it knows about. So our router that knows about other networks there at the local site will ping every single other network it knows about. And the first response it gets is where it sends the data. So it might bounce around quite a bit. I only drew 6 pictures there, but I think y'all are well aware there's more than 6 sites spread across America. So there's a lot of different channels that a signal could bounce around before it finally reaches its destination. Check all possible routes and send the data down the best available channel, which really just amounts to, it responds to the first ping. The first one to respond is where it sends the data. And a little bit extra stuff in there to make sure we don't have duplicates, like saying that it's coming from site A. So whenever site B pings every machine it knows about it, if it hears back from site A, it doesn't need to send it back where it came from. It's trying to get down the best route. So that gave us a way to basically survive the doomsday situation. No matter what's going on, maybe this line breaks, this line breaks, this line breaks, this line breaks. This line breaks, this line breaks. There's a lot of broken routes there, but from the mutually assured doomsday scenario, but there is still at least one route through our communication channel for the communication to reach its destination. So that's what's known as Internet Protocol. The original idea was called ARPANET, and then that extended to just we call that Internet Protocol. A nice simple way to assure we have a good communication channel. But we might be sending different amounts of data. This could change, right? Because different sites are trying to communicate with each other, they might have different amounts of data that they need to send at a given time. Site A might be trying to send 100 megabytes, and site B is trying to send another 500 megabytes at the same time and clog up the channel. So we need a more efficient way to break down the data. So along with that, there's another protocol we use called transmission control protocol. Or TCP. And TCP is a way of organizing our data. It breaks data into small packets with simple error detection and instructions to reassemble on the other side. So I'll do this in the picture. Maybe this is our data, right? 11100101101. Bunch of binary code that the machines know what to do with. So we have this data we need to get across the network. So instead of sending that as one big chunk, TCP is going to break that up into small chunks. And then each chunk gets sent independently. Or something like that. So we break whatever our data is, we break it down into a small size, add a little bit of error correction. Really, we just do what's called a checksum. We have a bunch of ones and zeros making up our binary data, right? So if we add all of those ones together, we're either going to have an even number or an odd number. So we can check on what it's supposed to be. Just all the machines involved can agree that, okay, we're always looking for an even number. So if this data right here comes in, 11111, that adds up to an odd number, but the machine knows it should be an even number, so it can at least detect that an error happened. And transmission is really, really quick. So whenever we detect those errors, basically the machine sends the signals like the data error, send again. Really, it's just error, send it, please send again, error, please send again, over and over and over again. So if you've ever sat there and waited on a website, like on their website, load it up, and it seems to be taking longer than it should to load, that's what's going on. The whole time the machines are in the background saying, oh, something went wrong, send it again, something went wrong, send it again, something went wrong, send it again. Probably based off the little checksum bits. Everything was supposed to add up to an even number and an odd number came in. So we know something went wrong. So we have that error handling. Then we have instructions to reassemble it. So we need a little bit extra data tacked on there. I'll put it on there. It was like the first piece. And then something that says the second piece and how it goes back together. And then some other information like, I'm just going to put a question mark here. Like, what software does it open with? What is this internal machine stuff? Is it something that shows on a graphical interface? What do we do with this data after we assemble it? So we break it up into pieces, add on these extra little bits of information, and then we have these small chunks that we can send across the network. And really, so there's extra. Okay. There's that extra bit that we have to find the best communication channel, and all that extra bit where this isn't all of the data, this is just a little bitty piece of the data, and this is the order it goes in, this is where it came from, this is where it's going, this is what software it opens with. All that extra little information adds up in all those little bitty chunks. So it was a lot of extra stuff. But the thought was really nice. And really by the mid 1980s, about 1984, 85, what we would call the average machine could handle that extra bit. By 1984, the average machine could handle the overhead that came with this And once the machines could handle it, it very quickly became the standard, and we haven't really looked back since. We put these two together. So transmission control protocol breaks our data into small manageable chunks, usually 1,024 bits at a time. Take 1,024 bits and send that with extra information on how to put it back together on the other side. And then we'll take the next 1,024 bits, add in that extra information, and send that. And we send each chunk independently across internet protocol. So if we have a big network like this, I'll put these colors back in here. Every data packet we send could be taking its own route through the network. This is probably looking like a mess on the video, but try to do something here. There. But each data packet, we break it down, and then each one finds its own way through the network, and it gets reassembled on the other side. Once the machines could handle it, that pretty much became the standard, and we haven't really looked back since. There's some other stuff, right? Like I pointed out that small checksum, like something went wrong, send it again. Y'all have all definitely waited on a website to do that. It's probably happened at least once in our Zoom call today, right? Because my video got scratchy at any point, or the audio. For some reason, Zoom.
Very rarely.
Occasionally it does, but yeah, for some reason, Zoom decides to cut the video before the audio, or the other way around. Zoom decides to take away from the audio before it takes away from the video, but that was just a programmer's decision on which one to back off of first if things got sketchy. But I'm sure everybody's seen that. And it's no problem on the website because transmission around Earth is fine. But what about like that camera we sent to Pluto? What was it? When it was passing Pluto, it's still going. It hasn't even hit a speck of dust yet, which is a great indication of how empty space is. It's going to keep going until it hits a speck of dust, which at those speeds will utterly destroy it. But it hasn't hit a speck of dust yet, so it's still out there going, taking pictures of stuff. But when it passed Pluto, they're coming up on Pluto and passing that. It took 4.5 minutes, or not minutes. It took 4.5 hours for that signal to get back to Earth, and that's one way. So for that data from that camera, essentially, there was a lot of other stuff there, but that was just to get the camera to Pluto so we could take pictures of Pluto. So to get our data from that camera took 4.5 hours. So if a simple checksum wouldn't work in that case, right? We wait 4.5 hours to say, oh, something went wrong, send it again, and then ask for more data. We need something fancier that way. It'd be 9 hours before it even resent the next set of data. And that would be unacceptable. For those, we have like error correcting codes, and there's much fancier things. But for any network communications around there, or TCP IP is really easy. We're in preview mode of networks, and I basically told you how IP network works, right? You have to do half of that on your homework this week. So really easy to implement IP protocol. TCP is not much different. Y'all will study it in detail in your networking class. It's called the Osi model. It's a highly organized thing. 7 layers, they all mean something specific. So when the data comes in on the other side, every machine knows exactly what to do, how to take apart those seven layers and put them back, and discard some of them that were for transmission. Look at the ones for the application, figure out where to put, what to do with it, and figure out where the actual data is. It might sound like a lot at this point, but it's fairly easy to put together. And y'all will study that in detail later. But those two protocols are really easy. They're fine for any communication around Earth. So once machines could handle them, we pretty much never look back at other protocols. We've just gone with that since. And putting them together, we break our data up into little pieces called packets. I guess that's an important term. break our data up into packets, and then each packet independently finds its way across the network to be reassembled on the other side. It finds the best path across the network, which oftentimes they will take different paths, which is one of the questions on your lab this week. When you'll ping some other machines and see how long it takes, or not ping, you'll trace the route you take to communicate with another machine. And then you'll do that a couple times to see if it took the same route, or if it found a different route the second time through, and little things like that. But that's sort of the core idea that I had wrote down here with vocabulary terms, some important vocabulary terms for networking to get us familiar with that. And everybody has to take at least one networking class. A lot of the degree programs, you'll have to take at least 2. But for our class here, it's, again, this is mostly a vocabulary class, and that was the vocabulary terms I had written down in my notes, and somewhat in context, the sort of thing you'll see on the weekly quizzes and all that. Does anybody have any questions about that as far as what we covered? Okay. I'm sure you have lots of questions about networks, because it gets a little more complicated fairly quickly. But that, I think, finishes out what I had on the list for today. Who else still here? Is Macy still here, or Michael? Nope, I don't see either of the names I wrote down, so I'll contact them later. I have a list of things to do with the advising side, so, and 2 names on that list are on our roster, but I don't see them here, so I'll just contact them later. It seemed an easy way to get out of a phone call. So a few different things. I'm going to put the link in the chat room again for those who weren't here earlier. The keynote from the NVIDIA conference this morning had some very, very interesting things. If you want to watch that, and that will be an option that you can use for the Module 8 discussion board. A way more interesting option. They had some really interesting things to talk about at the NVIDIA conference. So there's the link to the keynote speaker. I would recommend watching the keynote. I'm going to take out that thing where I ask you to watch in live time from the instructions. That was probably a bit unnecessary, and might have ended up with people accidentally clicking on some of the not free ones. And I didn't think about that in advance. It's like, oh, we should watch it later, and that way they're all free later. But some of them cost money for the lifetime ones, and I didn't think about that in advance. But the keynote, definitely some interesting things there. You can check that out. We have 50 minutes left in our class period today. My recommendation for lab time, please use our time productively. My recommendation would be to start doing some of those terminal things like we looked at before the break. Maybe just search for some YouTube videos, and not even work through it now. Just click on a few different ones and see who you like the sound of their voice better in the YouTube videos, and figure out which ones you're going to watch and get started on that path. Because no matter where you're heading in IT, that will be a very important skill. So you'll want to start practicing that soon, because operating system control languages are very, very large, and it takes a while to learn them. So you want to split it up and learn it in pieces along the way. Makes it a lot easier. Otherwise, that's everything checked off on my list for today. Does anybody have any questions? Okay, I assume a few seconds of silence means no questions. So y'all have a great evening. If you have any questions, let me know. As always, I'll be sitting here till 3:50. Text messages and Ivy Learn messages make noise on my phone, and I'll just be sitting here waiting for questions to come my way. Otherwise, I'll see y'all on Thursday. Everybody have a good one.